In this lecture, we are going to discuss about mathematical modeling and transfer function. So let's start with mathematical modeling. So whenever we want to study any system or examine any system, either we will be requiring a practical setup or a equivalent representation of that system. But to have practical setup always is not advisable. So in that case, that may happen because of various limitation like cost and other things. So in that case, we will be requiring equivalent system representations that we can have in place of practical setup in order to study that system. So one of the way of creating an equivalent representation of the system is with the help of mathematical model. So that will be a mathematical form of the system that we want to study. So we can define mathematical model of a dynamic system as the set of differential equations that will going to fairly represent the dynamics of that system. Now mathematical model can assume different form and that depends on particular system. So here system we can have like a mechanical system, electrical system, thermal system or any other system. Now because of the physics that involved in various type of system, we will be having different mathematical model, and that also depends on the particular circumstances or situation. So these are the factor because of which we will be having various model or different model for different system. For example, if we are having a mechanical system, so that system can be analyzed with the help of Newton's laws. If we are having an electrical system, so that system can be analyzed, or we can create mathematical model of that electrical system with the help of Kirchhoff's law. So in that way, what type of system we are having, based on that we need to see what type of physical law it is going to follow, and based on that we are going to create a mathematical model of that system. For a given system we can have a various model, so one model may be better suited than the other one. Also mathematical model is not unique. It depends upon the designer what aspect of the system he or she has considered. So based on that we will be getting a mathematical model of that system. So let's understand that with this example. We are having a rider who's riding this bike. In order to get the mathematical model of this system, first we need to create a model of this system that will be based on the element that are going to represent this entire system. So as this system belongs to a mechanical system, we can represent any mechanical system with the help of mass, spring and damper. So here let's consider M to be mass of the system, K to be stiffness of the system, and C damping of the system. Now what we can do, we can represent this entire system in block model in this way. So we will be having a mass M that will represent the mass of entire system. Then we will be having spring that will going to represent the stiffness of this system, and we will be having a damper or a dashpot which will going to represent the damping element of the system or a heat dissipating element of the system, that is represented by C. Now this is one of the model of this system. Now one can develop another model of this system by considering various elements separately, like we can consider mass of the rider and mass of this chassis separately, and this suspension system of front and back wheel separately, and also considering the wheel weight and wheel stiffness separately. So that model we can build in this way. We will be having mass of the vehicle plus mass of the rider. So now we are going to consider back and front suspension separately. So they will be having their own stiffness and damping constant. So say this is a back suspension system, so KS, and CS is the back damping element of the suspension system. Similarly for front we will be having stiffness as again KS, and for damping element we will be representing it as CS. So this KS and CS are representing suspension system stiffness as well as its damping property. Now we can also treat two wheel masses separately. So we will be having, like, for back wheel we will be having mass of wheel, and then for front wheel we will be again having mass of wheel. And now this wheel will be having some stiffness, so that we can represent here as kW. And similarly for front wheel also we will be having some stiffness, so it will be kW again. Now this is another representation of this system. So once we have converted a system based on various element in the form of block, now by applying the law of physics that it is following to convert and get the governing equation, that is nothing but the mathematical model of this system. So that we are going to see later on in this course, how to get the mathematical model of a given system. So now here we can see that if we obtain a mathematical equation or mathematical model of this system based on this model, it will be different than based on this model. Now we will discuss about the transfer function. So transfer function is a relationship that maps the input and output of a system. So if we are having a practical system, we can give an input and we can obtain the corresponding output. Now when we are not having the practical system, in that case we will be obtaining the mathematical form of the system, that is the transfer function. And when we apply input to the system, we should get the same output of the system. So here this transfer function, that is the mathematical form of the system, must behave in the same way as actual system is going to behave. So now transfer function we can use for a linear, time invariant and differential equation system. Now let's define the transfer function. So we can define the transfer function as the ratio of Laplace transform of the output of the system, that is the response function, to the Laplace transform of the input of the system, that is the driving function, under the assumption that all initial conditions are zero. So this is important thing that we have to keep in mind, that transfer function does not consider any initial condition. We treat all initial condition to be zero in case of deriving a transfer function. A linear system we can represent in a mathematical form with the help of this equation that we are having here. On a left hand side term represent the output and a right hand side term represents the input. Let's take an example and write a differential equation with the help of this generalized equation that we are having for a linear system. So we can write like a0 y say double dot plus a1 y a single dot plus a2 y, and that will be equal to a b0 x dot plus b1 x. So this is a differential equation for a second order system, and that is because of the second order differential that we are having here. So we can write it in a normal representation like a0 d square y by dt square plus a1 dy by dt plus a2y, and that is equal to b0 dx by dt plus b1x. So this is a normal representation of a differential equation. Now this type of differential equation we can write for any linear system with the help of this generalized equation that we are having. Now how to get the transfer function from this differential equation? So this equation we are going to get based on the physical law that system is going to follow. So based on that, by applying that law, we will be getting a differential equation which will be having this form. Now in order to get the transfer function, we know that we have to take the Laplace transform of output as well as Laplace transform of input, and we need to take the ratio of both. So that we can write in this way. So transfer function that is represented by g of s, and that will be Laplace transform of output upon Laplace transform of input. A very important thing is we treat initial condition as 0. So once we take the Laplace transform, we can write the equation in this form as a ratio of Laplace transform of output to the Laplace transform of input. That will be having this form. Whenever we are taking a Laplace transform of a differential equation, we need to always follow the rule of Laplace transform for a differential equation. Like if we are taking Laplace transform of say function d f of t divided by dt. So when we are taking a Laplace transform of first order differential, so it will be represented as s dot f of s minus f0. Similarly, when we are having a second order differential, so it will be equal to s square f of s minus s into f0 minus f dash of 0. Similarly, when we go to higher order like third order, then we can have s cube f of s minus s square f of 0 minus s f dash of 0 minus f double dash of 0. So this way we need to take the Laplace transform of differential equation. Now here we can see that the result is having initial conditions also, but the good thing with Laplace transform is that it treats initial condition 0. So here in first order this condition will vanish. Similarly for a second order system, these initial condition will vanish. Similarly for third order, all these initial condition will vanish. So we will be only left with a term that will be having s and f of s. Now let's discuss about the advantages. So transfer function use Laplace transform to convert a differential equation into a simple algebraic form. And when we convert a differential equation to a simple algebraic form, we are having various mathematical tools to deal with algebraic form, and analyzing system in algebraic form is more convenient compared to analyzing it in a differential equation form. Next advantage is, if we know the transfer function of any system, we can get its response for any kind of input. So analyzing a system based on transfer function is quite easy. Next advantage is that with the help of transfer function, we can get the poles and zeros of the system. These poles and zeros will help us in understanding the state of the system. Next advantage is transfer function will help us to study the stability of the system. So this is one of the major advantage, that with the help of transfer function of the system, we can check the stability of the system, how it will going to behave when gain of the system changes. Now disadvantage associated with transfer function is that it can only be used for systems that are linear. Then another disadvantage is that it does not consider the initial condition, and also transfer function does not give any information about the physical structure of the system. So how the system will look like, we cannot obtain any information regarding that with the transfer function. So these are the advantages and disadvantages associated with transfer function. So before ending, let's discuss what we have studied. So we have studied about mathematical modeling, and then we have studied about the transfer function approach. So with this, we'll end this lecture.